Okay. So if you don't have any open questions, then let's start with the next subject. So a thing that is often useful and often also requires multi-threading is networking. So today we will be taking a look on different ways how we can communicate between the processes on the network, and also how we can communicate between individual processes on the same host with other means. So let's start a new project. A normal console application this time. Let's call it TCP server. So first we will create a server application, and then we'll create a client which will connect to it. So first we need to include a few things. That is, in case we're using Windows, this will be the headers for WinSox 2. And one more. That should be all we need. And on Windows applications, first we need to start up the network stack. So this can be done with the ASA startup function. It takes a few arguments and specify the exact version you want to use, and we also need a helper variable to get some data. And after we've done this, we can start using network functions. At the end of our main function, we should uninitialize everything. This is done with ASA cleanup. And we return 0 for good measure. So generally when using the network, there are two common protocols that are used. One is TCP, which is like the main protocol in use often. It stands for Transmission Control Protocol, and the way it works is that it is a connection-based protocol. So you first establish a connection, and this gives you more or less a pipe between your application and the remote server, where you can throw in data on one end and they will come up in the same order at the other end. The TCP protocol guarantees the order of the data to arrive, and it also guarantees that the data will either arrive or the connection will be classified as broken if the data cannot be delivered. In contrast to this, you can also have the UDP protocol. UDP stands for User Datagram Protocol, which is a very simple protocol. It is just basically a small header that is attached to a IP frame that contains, in addition to the addresses which are already part of the underlying IP layer, just 2 ports. Similarly, like in TCP, there you also have ports, but it doesn't do anything else. You can send a packet to a remote computer, but there is no guarantee that it will arrive. There is no guarantee in which order multiple packets in the same computer will arrive. So if you need any level of reliability, you would need to create your own custom protocol on top of UDP that would then implement retransmission and other features as you need them. In the last years, UDP has become more prevalent in the networking space because it is more flexible than TCP, and also when you think about it, TCP was designed in a time where you had connections which were at their best measured in hundreds of megabits, probably even less than that, while nowadays you have connection speeds of hundreds of gigabits if you buy the right hardware. So there are aspects to how TCP was designed that is not entirely suitable for modern networks, and implementing something custom through UDP is in various applications more and more interesting. In normal lab use, you probably will only see TCP being used, as for most instruments you don't have very high data rates, and even if you have to some extent significant data rates there, usually a TCP connection should also be good enough. The main issue with inventing new protocols is that the way the internet as such is specified, the ISPs only route TCP and UDP traffic. If you would and some and a small subset of other protocol types, they usually would not route something completely unknown. So at this point, the users are limited to use UDP if they want to implement something custom. Okay, so let's continue here with creating a TCP server. We will need some variable to hold some return values, and we will need a socket which will be listening for incoming connections. With the function socket, we can create a socket object. I think we are missing an include. It should be all we need. Do I have a typo? Yes. Okay, so if I specified that it's a IP-based connection, and then we can specify that it's a stream connection, and finally which exact protocol. The way the network is structured is you have multiple. There's a question. We are not done with Qt yet, so later during this lecture we'll see how to do the same thing using Qt objects. So Qt will continue being used throughout the lecture until the end. But many things, it's good to see them in the very basic implementation first. Okay, so back to the subject. So the way the network communication is structured, it is usually organized in layers. So at the very beginning you have the physical layer, so just the electrical aspects of the connection. Then you have the Ethernet layer, where you have the data that go over the electrical connection, so to say, and on top of that you have the IP layer, and on top of that you have your protocol layer. So when you have here, for example, when we specify AF inet, that means that we will be using IPv4, which you know it's made up of 32-bit addresses, and as probably is already known, those addresses are running out, at least on the global internet, so there are not enough address available for the needs. So there is also a new version of that protocol called IPv6, Inet6, which has 128-bit addressing, and it's getting more and more used. And on top of that, in the next level, we have our TCP or UDP protocols, or other protocols which are built on top of the IP protocol. The internet as such routes only the IP traffic. So for example, when you send data to your router, the IP data are put on Ethernet frames which have their own format. They are then sent over the wire to your router, which receives them, and then sends them further to your internet provider. What happens on the Ethernet layer is not relevant, it is not relayed. And the internet itself, when it relays data only based on the IP addresses and not on anything else that would be inside the frames. Once those data arrive at your computer, the next level of the protocol is being analyzed. So in this case, TCP and UDP, as already mentioned, contains so-called port numbers, which allow you to specify which applications on your system will actually receive those data. So your computer has an IP address assigned, or multiple, depending on how many network cards you have and in your network topology, but in the simplest case it would be one. And the whole computer will receive data based on the IP, and internally, based on ports, the operating system's network stack will then decide to which applications individual package should be further routed. And which ports are used is quite simple. Just when you start your application and set up a socket, then at some point of the socket creation you have to specify which port exactly you want to use, and then this port will be reserved for your application. Another application at this point will not be able to try to reserve the same port. So it's at this level quite simple. So we create our listening socket. At this point it is just created with some configuration, but it doesn't do much. Now we need to prepare some additional data. So other info name, comma, we clear this. So this is a data structure which will contain address information. Maybe is again init. Socket type is again stream socket. What's next? Protocol. STCP. And we can set some flags. Set it to passive. Info get other info. Let's select something semi-random. Now we are binding our listening socket to a specified port and a specified address. So we have not specified an address, so it should normally be then bound to all addresses that are available on the computer. You can basically just specify one address and the socket listens only on this one IP address, or you specify all zeros. This means it will receive incoming connections or data from all the addresses that the computer has. Address, comma, result, and then bind. And finally we have to start listening on the port. We should of course check for red being an error, but we are lazy, so we don't do that. And we can specify a backlog number. This will so when incoming connection is incoming, then the connection needs to be accepted by the application. The application could, based on the address of the incoming connection, decline it outright, or it might accept it and close it later, etc. The backlog specifies how many connections the operating system will keep pending are not yet accepted, before it starts automatically reject connections on its own. So if you expect a lot of connections coming in, then this should be a large number, and of course you should try to write the application such that it will accept or reject applications quickly. So here let's specify 25 connections. That's more than enough for our use case. So at this point, when we put here a breakpoint and run the thing, then inspect. Alright, we forgot one thing. The whole network functionality is located in a set of DLLs to which to interface to we need to include a library. Since we are using the functions directly without importing them manually, it's the vs2_32 library. Now it should build fine. And now the firewall of Windows is asking us whether we want to allow incoming connections. We say yes. And while we sit here in the breakpoint, we can use some advanced task manager to inspect our application, TCP server, sockets, and we see here there is a socket set as listening, local address all 0, so it will accept connections from anywhere, and it's on the port which we specified, in this case 27015. So that is fine. Of course, now when we continue, the application will just terminate because we don't do anything. So what we need next is we need to start accepting connections if there are any. So for this we just create a loop for endless loop, and in the loop we need a variable to receive the incoming connection. So once the connection is accepted, it will become a socket of its own. Need of course to accept the previous connection, and then here in adr and adrlen we could, if we wanted, receive the address from where the connection came. Since here in this case we don't care, we just use null. In many simple applications we don't care from where the connection originated, we just care to receive it and then talk to the other end and see what they want, or so on. Especially if you have some devices which you are talking to, or which connect to your software, you don't assume that you would need any sort of blacklisting or whitelisting based on address ranges. That should be done by your organization's firewall, that just nothing comes in from outside. Okay, so here we should check if that was successful, because it might not be. So if this is an invalid socket, then we need to read the error. VSA get last error, and we continue to the next application. As mentioned, everywhere where we have this thread, we should actually add a few lines in case of a failure, print the error, and so on. But here we just want to have this value so that if we put a breakpoint on the next instruction, we can inspect the error manually. So at this point, we have here a socket which is open, which can receive data. It can also send data if we want to, but we haven't done anything with it yet. Before we do, one more thing. Of course, before we terminate the application, we should close the listening socket. This is generally good practice to close resources, even if you know that if you terminate the application, the operating system will clean up everything for you, because if you want to reuse your code later somewhere else where you don't just terminate quickly thereafter, then your code, if it's architecture to have resource leaks, will have resource leaks, and then will make your long-term running application crash. So it's better to be correct about such things and always clean up resources, even if you expect in your current use case this not to be relevant. Okay, so now one thing of course we could do is we could start here in this thread reading or writing to the socket. So in the simplest scenario, we could just write something to the socket. Send socket, comma, we need something to send to. Let's be super lazy about it. Test, comma, 4. Like, that's really not the way things should be done, but it will work. And then we just close the socket. Although it might be that if we close it instantly, that it will not purge the buffer, so the send will not actually be sent. So let's add a short sleep so that we can be sure that the network stack has sent everything. And of course, if we get more than 10 sockets per second, then we will start up filling this backlog. So this is really just for a very quick test. We need something where we could to communicate with. So let's copy some application that is good enough for the job. Maybe Putty. It's a very simple telnet client. Okay, so we start our application. Okay, the application is now running, waiting for something to happen. And here we go on telnet. We should choose a easier to type port. And if we want to address our own computer, we can always use the 127.0.0.1 address. So it's the local host address, and on every computer it points on the computer it is on. It never points on a different machine. So this is quite nice. And as you see, we have received the text test, and Putty is complaining that the connection was aborted because Putty would not expect the remote site to close it. Since it's a terminal application, it won't be the one participating party to close the connection. So here we just close it. And now, how can we make this better? A common approach here is just to use threads. So instead of blocking the main thread, as soon as we receive a new client incoming, we will create a new thread. If we want to be particularly efficient, we could actually go with having like already a pool of threads ready and waiting for us to do something. But if we want to do everything by hand, then so it's simple. We'll call it client process and void param or lparam. Okay, so we have our typo, our thread processing function, so we specify it here. Then we can specify the param, so we obviously just use the socket and pass it on. Creation flags none, and here we don't care for the return value. And we close the handle since we don't need it anymore. This needs to be casted to the right type, LP void. Okay. Good, and then inside our function here we can then do whatever we want. So we of course need to retrieve our socket. Basically just cast it to the right type. If you would, for example, here have retrieve the address, then it would be a good idea to have the data put into a structure which will then pass instead of just the socket, so that we can have more arguments, but for now this is fine. And now we need again our ret variable for some data. We will make a new endless loop. The loop will run until the socket is not longer operational, and once that is done, we just close the socket and we'll just create a simple echo server. So the server will just receive data and then send them back to the sender. So for this we need a buffer. Let's make it 1 page in size. Int e. To receive data from a socket, we use the receive redsv function. It takes again, of course, the socket as an argument, and then the buffer. And the way most of the socket functions work is very similar between Windows and Linux, as they all go back on a common standard implementation of Berkeley sockets. So of course there are specific functions like VSR startup is a Windows specific thing, but just creating a socket or binding, listening, redsv, all those things are available also when you are building on a Linux, just the same. So you don't need a lot of adaptations if you want to make your code platform independent. Now we check if we have received something. So if the function will return a positive value denoting the amount of read bytes if it read anything, or it will return something less than something negative if there was an error, in which case we break. So if received no longer works, then we just break, and we can again just grab the value of whatever is in red right now, so that we can inspect it if we want to. Small typo. Okay, so the else case is of course that it's either 0, meaning there was nothing to be received, although the redsv command should be blocking unless you configure it otherwise, meaning that it will we will stay in this function until either the socket breaks for some reason and the operating system decides an error is occurred and the connection is broken, or until some data have been received. This behavior can be changed such that the redsv will be non-blocking, in which case it will just instantly return 0 if there is nothing, but here in our case we want to be flexible, so we will check for it not being 0 even though it is blocking. So if it's not -1, it should never be 0 in that case, but it's good to test. Now we just send back what we received. Send looks very similar, so we can basically just copy the whole thing. We just need to change one argument. Of course, instead of sending the entire buffer space, we send only the amount of bytes we have received. And of course the way redsv works here is that it will receive only the amount that we have specified. If there is more data in the buffer, then so in the operating system buffer, then we need to call redsv multiple times. You could, for example, check if redsv is equals to buffer size, because if it is, then it's likely there is more, and then call it again. But since we here have a quite simple application, it's fine if it will be called in the next run of the loop, so we don't need to reconstruct the entire data to be consistent. So we can copy this here. There's one thing we should here look for. If this equals this, I would block, and this means that we tried to send and our send buffer is already full, so it's technically not a connection failure, but we have just exceeded the amount of data the operating system can cache in its buffer. The size, of course, can be also configured by setting different socket options, so we can specify how much buffer the sockets should have. In this case, we should actually retry, but for now we will just continue the whole loop, and that's it. It is not technically correct because the data that we failed to send from the buffer will be lost. But since this is a very simple echo server, we don't care for this aspect of the correctness, and we need to of course return something here. let's return 0, we don't really care for. So again, the application is running, we can monitor it here. So we see that it has one listening connection, one listening socket. You can copy the value. I can telnet. You can also use localhost. Let's save this in case you want to use it more often. Now if we open it, everything we type, so if I type 1, it types 1 because I typed it, and then we receive a 1 from the other end. So we could disable local echo. Change session config. Local echo force off. Now we only see what the other side sends to us. And here you see that there are now two sockets. One is the established connection between localhost and localhost, and one is the listening socket, which is listening for additional connections coming in. So we can connect as many connections as we want, and they all will, each of them will get an own thread and an own socket. So as you see here now we have 3 established connections, and if we look on the threads, there are a couple other helper threads, but the important threads for us are those 3. And if we close one of the connections, then the accompanying thread will be terminated. Should be terminated actually. It's okay. It's not doing what it should. It didn't properly terminate. Why? This gives us 0. It should give us an error and not 0. Okay, let's quickly. We could check if this is of course or 0, but that is not how the behavior should work. Then we will see here what error will become if there is nothing to. Since we open the threads here, one of the files is being used by the other tool. That will the lock will be released automatically after a short delay. It is blocking. When we close it, also return an error. Well, let's leave it like this, and now it will be. It should. REST should return us an error when we close the connection from the other side, but it doesn't. So I'll look into it later why this is. For now, let's just again create a few connections, as we did before. We have our connections. I didn't save the session, so the echo is turned on again. And here when we go back to our, here we see again our 3 threads, and then let's terminate one of them. And now as you see, the thread is going away, so the resources are being freed properly. Okay, we can of course create now an own client application, so we can let this running. We could also make this printed the things that come into the console. That might be also funny. So can buffer. Just that it's not null terminated, so we'll throw is equals 0, and here let's add a +1 and here -1, so that we have 1 byte spare. Set it always to 0, so that printf will not improperly keep printing past the end of our string. You see the term? Sometimes it's printing random characters. That's interesting. I know. We should maybe change this slightly. Just to ensure that we don't try to interpret what is inside buffer, that we just print it as it goes. That should make it more robust. And here we lost the connection, so let's reconnect. We get some characters at the beginning which we don't really expect. Let's put a breakpoint here and reconnect to see what's happening. Okay, it seems that the putty is sending really some additional configuration parameters which we don't want, so let's simplify this. Let's take something that is really so basic that it will not interfere with anything. Just use a command line telnet client. And the port was this one. Of course, we need to start the thing. And this really does what we want. It just sends whatever we type. Putty, being a full-blown terminal emulator, will have for certain scenarios different escape sequences which it will send to the server and expect a certain behavior. Here, this being a very trivial server, it of course doesn't interpret those in any way, but using this telnet connection here, we cannot even break out of this easily. I don't think we can actually quit it. Basically, it just sends whatever we type, and even Control-C is not being accepted. So basically, if we would send quit, the other side would need to understand it and close the connection. So for simplicity, we'll just terminate telnet and the connection is gone. So yeah, but this is not a big annoyance, since we'll just now create our own client. So having our own client will give us the ability to define whatever behavior we want. Okay, so let's go to TCP client, create new project, command line, copy a few things from the other project. Just the content, this part will be different, and we can also copy the library include, because we also will need to insert the library in the other client application. So the client is quite simple. Actually, we don't even need to delete so much. We just rename this to client socket. So this remains the same. It's the same type of socket. We just want to connect to something instead of to listen to something, and we will need again to get the address. So the port, of course, stays the same, but we need to specify the IP we want to connect to. And one thing you may have already noticed from here, although now we of course don't see it, is that once we have a established connection, you see here that there is like a remote port. So in order, of course, for the system to know how to associate the data, if you create an outgoing connection, it will get a port number on your system automatically generated. This operating system's network stack will just choose the next best high range random port that is 3, so that when your computer receives packages at a certain port, it knows where to relay them. So here in principle we could specify an outgoing port as well, but we don't want this. We will just leave this out on the automatic behavior, as there is no benefit for us currently to specify a outgoing port name. And now of course we use the connect function to connect the socket instead of listen, since we want to connect obviously. And here we just provide again the result address and the address length. So now the thing knows where to connect, and of course the rest of the behavior will also be different, because now we can do whatever we want. So we could send something again, for example like we did before, just test, and we can, for example, wait for the return. So char buffer can 0x1 2 3 plus 1 is equals, we initialize this with zeros for good measure, since we want to print it later. And then we use redsv that we can copy from here. Could add here some initialization as well. It doesn't really matter since we are nulling it, but that is okay. And at this point we can already close the connection. So we might want to add some. No, we don't. We don't want to wait. Language right. So our we minimize this, make it at least slightly smaller. This will minimize, then we have here our server, and when we run it, this should print test, and our own application should also print the test reply that it got. So this printed test. Here it didn't print. Oh yeah, we forgot the print line. Let's copy the print line as well. Now it will print the test that came back. Test. So as you see, it's quite simple. You don't need much code to create a connection. And it is quite convenient to use TCP, because as said, you can just throw in data on one end, and on the other end they will arrive at the same order without any problems. So you will not need to write any own more sophisticated management. One thing that you might need to write yourself is if you want to have some sort of data rate limitation. But usually I would not expect this to be needed in the typical applications that you would expect in a laboratory setting. So usually you would just want to send or receive as fast as you can, and that's it. So at this level we can leave this, and now we can, for good measure, try to do the same using Qt. So let's close the applications and create a Qt application. Create new project, Qt. Let's go with a widget application, since it will be nice to be able to add some buttons that do something. QTCP server, let's call it. And later we'll of course also create a QTCP client. Here now we definitely need to add Qt network. Precompiled header, we don't care for the icon, finish. Was it clear so far? Do you have any questions? Okay. So we have our QTCP server, and well, the thing is just an empty window at this point. I just quickly compile it so that the precompiled header is created and subsequent compiles will be faster. And let's see how we continue from here. So Qt offers a class called QTCP server, which we can use. We could either create first an own object which would have the server functions, or we just use it directly in our UI window. And I think we should try to keep things simple, so let's keep it here in the UI window for now. If we later want to make it more complicated, it's more convenient, but it's not good design. If you would later want to use the server somewhere else, then it would be work to divide it apart. Let's create our own class. That's a bit more work, but more illustrative. So let's call it, let's see, my server, capital M, from QObject. Since we're using Qt, it's nice to derive everything from QObjects. Plus, we will have things on our my server which will need to be able to send and receive signals and slots. Okay, include TCP server and TCP socket. Okay. Let's create a constructor. For a destructor, we don't care. We need a few slots. On new connection is triggered when there is a connection pending to be received. So if we go back here, as soon as accept stops blocking and some code is to be executed, this will more or less be the point where the on new connection slot will be invoked by Qt, so that we can do something with the thing. Okay, that should be all with regard to functions. Of course, we need our QTCP server. And similarly to here. So here we have created a socket for each operation. Sorry, a thread for each operation, for each socket. But this is not necessarily necessary. Since Qt has this slot mechanism, we can asynchronously react to things that happen. So here we can add just a Q set of QTCP sockets. And if we want to do something, we should then of course add some more signals. So there are two strategies. We could create an own object now called my client socket, which would do something, or we can have all the functionality in this my server, which is I think a nice demonstration of the async functionalities in Qt. So let's go with this. So there's on disconnect, which will be triggered from the socket, and put on data, which will be triggered if there are any data to be received from the socket. Okay, so we have four functions which we need to implement. And in this thing we of course need to create the thing, so Oh, that's not good. The file names, I didn't want the C to be there, so let's quickly fix that. It's actually a very fast fix. It's over here. Okay, so now we need to create a new server. And we could, in principle, make this a not a pointer, but it's already started like this. Let's keep it like this. Okay, so we have our server instance, and now we need to tell it where to listen to. And in Qt, as you see, this is all quite a bit more simple. You don't need to write that much code to get this to get to the same result. 27015. So you just specify that address any, or you could provide a qhost address containing a given IP, and you specify the port, and it's already listening. This is quite significantly more convenient than how you have to do it if you do it manually, where you need to create helper structures and so on. So Qt is really nice. And here we can use qtcp socket stern per socket is gleich server small p, and this creates for us a completely new qtcp socket instance. We just need to use this next pending connection function. So as soon as we call this function, Qt will create a new instance of qtcp socket, assign the new socket to it, and give it to us. So it's very nice. But of course, for this to work, we need to connect the slot. So connect per server, comma signal new connection to. We could use the new syntax. That's a bit more foolproof. New connection this way. We are typo proof with this, comma and of course here, once we have the socket, we want to connect the socket itself with the two functions we have here on this connected on data. Disconnected and ready. Read ready. That's small bug. The ready read disconnected. So we have specialized signals disconnected and ready read, which are triggered on these events. So data, as mentioned, means that we just have data which we can read from the socket, and disconnected means that the socket is no longer operational. And what we can do is here we can use a function provided by Qt called just sender to retrieve the pointer to the object on which the slot has been invoked. So in this case it will be the socket itself. Also, we forgot here one thing. We created here the sockets set. So let's insert our socket to it. And here on the disconnect, what we can do is now we can remove the socket from our set. So socket punct remove, and the socket needs to be disposed, so we delete later. We cannot delete it instantly since it might have some internal things to do after it has emitted this slot. And then now of course we need the what we are interacting with, and now we can read everything to a byte array. Use the read all function, which we have already seen, which just reads all the data, and then we just send the data back. Alright, he's right. There is a dedicated send function, just a write function on a socket like this, and we can debug the data so that we also here print to the console whatever we have received. Okay, that should already be working. Let's run it. Why is that complaining? That should not be complaining. Okay, I'm free of typos. We don't have pserver used anywhere. This is a valid object that should work. That's weird. To see if we need to include set. Yeah. Okay, so the error is somehow misleading. The problem is that it doesn't know what a set is. Qset. Huh? That should take only one argument and then takes only one argument. TCP socket we have defined as well. Then it's complaining again there. We have called our class TCP server. That was that's unfortunate. I wasn't thinking about that name conflict when creating it. We just add GUI to all the names. That will resolve the issue. And we should rename the files as well. Again, we have a connection, so now we can connect to it. Okay, something's not right. Server. It complains that server was not initialized. Oh yes, of course. I turned it into a local variable here because I just copied it from the top and forgot to remove the type. Now it should work. Okay, we already have the connection, and if we start typing things, you see it arriving in the console here. Also, we see again that PuTTY is sending a whole list of escape sequences to configure the terminal, which for our use case is not what we want. And here, as you see, we didn't need to create a own thread, and depending on the amount of data we had to handle, our server could be implemented all in one thread, at least from the viewpoint of ourselves. When we of course run it again, we will see that there are a couple threads created in the background by Qt. So is our server here, QTCP server threads. So there are a few. We have one created here by the Windows socket system itself, but this one we would have normally as well. And the rest, let's see on the call stack. Is there anything interesting? There is nothing particularly interesting here. We have here another thread which was also created by Windows. So I think these ones are all just loaders, so they should disappear after some time. So it is quite a different approach. So they might be also using a thread pool. That's why we have so many threads. We can debug this or test this by just putting a breakpoint before we create any server, so that we see how it looks then. Yeah, so we see most of the threads would be created automatically in any case, and then for us it does not need to actually create much more than the one additional WinSock thread internally. In principle, you can use the Windows socket mechanism also asynchronously manually. So similarly to how we did it here, was it here where everything is blocking, these functions could be set to be non-blocking. There are also a couple more non-standard read and write and listen functions, also such ones which trigger events, and we could create an own event loop and an own mechanism to not need much more threads than just the one created by the WinSock system in the background. But this would of course be significantly more complicated than this already quite convoluted example in comparison to how little code we need with Qt. So it is quite convenient. And as mentioned, of course, whether you want one thread or multiple threads would depend on your use case. So if you would have, for example, something that reads a lot of data from slow media and can lock up and sense it, then you would of course want a multiple thread. So you could have your server, and as soon as you get this thread, move the as soon as you get this socket, move the socket to a different thread, and then still implement one thread per client. In this case, it would be, for example, quite useful to instead of a set, using a map where you can then associate the socket with some helper object, depending on how you want to design the whole mechanism. But now let's go to the next thing and create a Qt client. So a client is even simpler in Qt, but we of course should try doing it. Qt widget application, QTCP client. We need to add networking, and this time we will add GUI here instantly so that we don't run into the same problem, although there is no TCP client object by default, so yeah. Now it's kind of unnecessary, but we just do it for good measure. And since we have a UI, we could create a button that will just send some data. Although for status we will just create our own client. So new class, my client without the C in the file name, Q object. And for the client, in principle we could also derive the client from QTCP socket, but I think it's more elegant to keep it separate, so QTCP socket again. Here we will copy a few things. Toastone. No, that was one line too little. One slot as well. No, better than this. So it's sorry, QTCP socket, then per socket. And let's copy those functions just for good measure as well, even though they will be much more simple. We'll only print the one will print and the other one won't do anything. So client, let's copy more. Copy this as well. The disconnect function doesn't do anything, and this function just prints it. And we also need to retrieve the socket, since we know what socket it is, since there is only one socket here. So socket is okay. Yeah, so we only and we need to send somewhere. So we will add that. No, we need one more connection. We want to know when we have connected on connected. That's of course a good practice not to pre-queue any data, but sit in the unconnected slot, and then from there we just then write here. You will need again a few connections, so for expedience we can copy them from here. So ready read is not interesting. We want well, no, let's leave it. But we want the connected. Right, so let's run this again so that it's running already in the background. Let's go to client, and one thing missing, we need of course to create an instance of client so that it can do anything. So we go to our client UI. to see here the output. So when we run it, we should see testing both outputs. Did it work? It did not. It did not connect. Oh, we forgot to connect. That's of course a good reason not to connect. What was the port? This one. It won't connect if we don't connect. It's connect to host. Since they used the connect function name already for the all slot connection mechanisms, now to connect somewhere we need the connect to host. And as we see here, it worked. We get the test back, we send the test, so as you see it becomes quite more convenient when using Qt. Okay, any questions at this point? Okay, no questions, then let's continue. Can close this. And the next thing I would like to show you is how to use UDP. So as mentioned, the difference is that we don't have a connection as such, when we just have a socket where we can send data in and out from. So we will now need to create a project which well, basically two copies of the same project. Or we like call one of them server and the other client, even though the sockets are doing more or less the same thing. Since starting two instances of the same project is a bit convoluted, let's go with creating two individual simple individual projects. And for expedience, let's go with a console application. That should be easy. It should be simple enough. So UDP client 1. The next will be UDP client 2. To add network. Good. So the client one will have more the server role, so it will receive something and then send it back. So for that we'll need a class, so that we can connect things. Let's call it UDP echo. Base class just QObject. Okay, so QObject. And again we need a few slots. Packet in UDP terminology is called a datagram, and we of course need to here the UDP sockets. Node Q UDP socket. Okay. So we have the socket, now we need to bind it to a port. So tell it on which port to listen. Well, listen on which port to receive datagrams. And let's go for port. Let's go with 1, 2, 3, 4. No. Let's go with a more abstract port like we had here. We'll just make it slightly different. Okay. Of course, we don't need to connect our socket. Reference. Oops. Read, comma, this, comma, reference echo on datagram. Right. Void. Right, since we know it's only one port, we don't need to do much, so we just need some buffer. Have a buffer. Host address. Since we want to send it back, we need to where to send to with the TCP socket. We did not need to be aware of which address the other endpoint of our communication has, because there the socket itself knows it automatically with UDP. Since when you have incoming packages, we need to always check from where the package comes in. Socket read datagram, and as you see, using UDP is a slightly bit more complicated in Qt than TCP, since there is no read all function which would provide us with the required host information. At least there wasn't in the past. We can quickly check if they have added it in the newest version, but I don't think, no, they did not. They just over it. So there is no nicer function. We need to use a buffer variable. We assume success. We should test for error, but in this case it's unlikely. And in QDebug we just now print our input data, and to send them back we use socket write datagram. So the way in Qt most of the objects which can be read and written to are designed. They are all derived from a QIO device, and in fact the QUDP socket is derived from abstract socket, which is derived from this QIO device. A TCP socket would also be derived from the QAbstract socket, and this QIO device has this read, write, and so on functionality implemented on it. And here, unfortunately, the way this works is that for datagrams, they break with this nice mechanism, so you cannot use UDP sockets in the same convenient way as you could use a TCP socket. So, for example, in Qt you could have a function which takes a QIO device and then sends data to it or talks with it, and which device you plug in, it doesn't matter. It can be a socket, it can be a file, it can be a pipe server, it can be anything basically. You can also create like an own QRO device which will take another QRO device as a proxy and then do encryption inside it. So this quite flexible mechanism, unfortunately here for the UDP sockets, is not functional. So that is something to keep in mind. So let's run it. And unfortunately we cannot test this with PuTTY or Telnet since they all use TCP. So we now need to implement our client too. And only once we have finished this we can then test whether what we did is functionally correct or not. QTCP, no, UDP, client 2, create. Network and core, that's all we need. Okay, and to mix things up, we will here just use the blocking, the way we can do it blockingly, let's say it like this way in Qt. So Qt, while it is generally architected to allow you to easily implement things asynchronously, so that you have your signals and they just wait for, so you have your slots and they just wait for signals to be triggered to then do something in the main thread and then return to the event loop. Here you might have of course use cases where you want a blocking architecture, and with Qt this is possible just as easily, if not easier. Just need the right include here and QUDP socket stern per socket / new socket. Now we need to bind it to a port. Let's take a port slightly above what we had before. So here we had this 5, so let's go on below. Let's go with 24 instead of 25. We cannot bind to the same port as already mentioned, then the operating system will reject the operation saying that this resource is already allocated by a different application, or technically it can also be blocked by your own application, by the same application. So even if you are in the same process, you cannot bind two sockets to the same one port. What you could do is, if you specify a port and an address, you could use the same port but different addresses, and have two sockets which listen on the same port, but one on address 1 and the second on address 2. One thing you cannot do is, like, you cannot add a third catch-all socket for any addresses which are not yet used. So you either have a catch-all for all addresses and do your own dispatching, or you need to list all addresses you have and then connect to all the addresses, or listen on the addresses manually. So there is a slight limitation of flexibility, which is not so bad because it adds some determinism to your mechanism. Byte array, that will be the data that we want to send upstairs typo. Let's call it test and let's fill it with test. Then we need the address q where we send to. Let's call it to 127.0.0.1. Another typo. Then we need port QU int 16. The ports are short numbers, so from 0 to 65,000 something, or in hex notation 0FFF, and generally the numbers below 1,000 are to some extent already taken by different known protocols, and the numbers above a couple 10,000 are usually used for to pick random ports for the operating system. So if you want to use some own protocol and create a listen on support, it is good to use a number between 1,000 and 10,000. But obviously you can pick any number that is right now not in use. So there is no hard restriction on that. just things which are customary. Here we of course need the port of the other end of the connection, so it was 25 at the end, and that's already all we need. We can just send something, so we don't need to create a connection, wait for the connection to be established. We just write datagram and we hope for the best. So it's comma 2 comma port, so it's just a send and forget sort of arrangement, and as mentioned, we have no guarantee that this data will even arrive. So on the internet or generally on any network, the different components have buffers which are limited in size. Even if it's just your local switch, it will only have like a meg of or 2 of memory. The idea is generally that since the packages are only a kilobyte or 2 in size, that they will be very quickly relayed such that they don't need to stay in this memory for a long time. So that's why such small amounts are more than sufficient for normal home use. Of course, a big commercial server with 10 gig or 100 gig will have much more cache, obviously, but at the same time it's very fast memory, so it's expensive, and it's on chip, so it's not something that is like separate that you can easily upgrade. It's usually just one chip with certain fixed amount of memory, and it's just doing all the switching. And of course, if you send more packages than can fit into this cache, then it can happen that one of the packages will then just be discarded. And especially if you are sending things over the internet, then package drop is to be expected. And the question is not if, but how many packages get lost. And as already mentioned, TCP intelligently can monitor for these package losses. Basically, it works like this. It sends a package and it expects to receive a acknowledgement package in a certain time window. If it doesn't do that, then it sends the package again and waits again, and it repeats this 3 or 4 times depending on the configuration. And if it doesn't manage to send anything anymore, then it considers the connection lost. And of course, there is much more complexity, since how many packages you want to have in transit will have a large impact on the speed of your communication. So usually TCP will just start with 1 package, then it will send 2, then 4, and so on and so on. And when it experiences some packet loss, then it will reduce the amount of packages just that it tries to have in transit before having them acknowledged, and thus and so on. So these congestion control mechanisms are not very complicated, but also not trivial. And with UDP you don't have anything of it. So if you have just a device plugged directly into a network card, and the device is made to handle a certain data rate, then you can expect that there probably won't be data loss. But as soon as you have some more complex network topology, you can always run into a situation where you won't be able to get the packages transmitted, or you can even run on your own system into the same limitation that you can, if you just keep writing datagrams at some point faster than what your computer can send physically out, then you will run out of buffer space on your network stack, and then the data will be dropped as well. So as just that you know, just sending something and forgetting about it is not a reliable strategy by any means. Now we can use the function wait for ready read, which will just block until the socket will become readable. And at this point, what we can do is just copy that until here, and that should be already the whole implementation. So we wait for ready read. In principle, this will just lock, and if we would have a signal or a slot setup, then it would just fire this slot. But here, since we are not connecting anything and instead waiting, it will just wait until something comes back. And in this case, it will wait forever. There is no condition where this normally would break, because we are not waiting like with TCP for data from one certain remote party, but we're just waiting for a packet, and a packet from someone can be just sent at any point in time. There is no abort condition. It may abort if we would use a task manager to close the socket forcefully, but that's not well. That will basically yield just undefined behavior, because there is an expectation that some third-party application will be closing your own sockets just like that. So this can be done, but I also don't know whether you can do this on Linux easily. You can do it on Windows with this tool, but I'm absolutely not sure if this would work in any way, shape or form if you would try to do that on Linux. If they have the API to kill another process's socket. Of course, internally that's a different story. You could find out the socket handle for your Qt object. They are usually providing functions to get access to the underlying operating system elements, and then you could shut down the socket from a different thread, for example. So, but these are all exotic scenarios, so it's not something that one would generally expect to happen on its own. Let's see, we have one limit. Okay, we need to change this here, especially port, since we don't want the conflict with the other port. And in principle we know that this will be just the other end, but we know what the application doesn't. So let's run it. We of course need to allow it as well. Okay, it did not. It crashed somewhere. Let's see what's wrong. Buffer. It didn't like buffer. We had len. Oh, len was -1, so it failed to read. Why did it fail to read? Probably because we didn't have the permission. Like when Windows asks you whether you want to allow it or not, it's not blocking to the underlying application. The underlying application gets a access denied, and if you say yes, then if you restart the application, then it will get a permission to do something. Okay, now we get a different. It's at the same place. That is unexpected, because this should be blocking until the thing is sent. Let's see if we receive anything on this end. We do not. Did we manage to open the socket properly and bind to it? It also can be a problem, source of problems. Okay, now this socket is properly connected. As you see, when you are using Qt, it opens two sockets, one for IPv4 and one for IPv6 automatically. Older versions of Qt did not do it, and I think when we have here this address any, we can specify that we want only v4 or only v6 addresses. I'm just wondering why this is not working correctly. Bind to a socket, we send something and then it should be waiting here, and it is not. We should see what we get from Datagram, whether that was successful. This one was successful, so then, and we send it to port 27025 that we should have received here, but we did not. I just had a breakpoint, but I don't think this will help. I don't think we'll reach that breakpoint. The problem might be that if this is not blocking as it should, that then what we get is that it doesn't manage to run long enough to send the data out. Does not have it has a timeout, but the timeout is not set. Let's see what we get returned here, but we should get in this case returned that it didn't work, so it should return false, but it returns true. This is This is not this is not how it should work. There is like no other wait function. I mean, we could it's also not producing any error logs here, that is, which would be helpful. I mean, we can just go with turning this also into a own class, but then the question is still why this wait for ready read function is not locking, because it should be waiting for 30 seconds until it decides to give up. We'll also put this in the loop and see if we see then something, but I don't think this will work also. Oops. Also doing it like this will require to check here if this is -1, so if this is only when it's more than 0, then we do the rest. Now it's waiting in the loop. The first time it didn't. Something is wrong. 2 and 4. That should be right. The right datagram was also successful, but this end did not receive it. Oh, there is something failing on this end, because this was not we did not we forgot to start this end of the connection. What was the name? UDP-echo. It's okay. That was a small oversight, and now it works. So we get test in both. So we sent the test and we got the test back. I'm still not sure why it ran over the first thing here, because it kind of shouldn't, the first event should not have triggered. We can test again by just sending. Interesting. It behaves strangely, because whether we send or not something, it should not fall automatically into this case. If the other side was not working, then we should have been just blocking all the time. Now this works, of course, fine. Let's try one thing. Let's close this, because if we send a package to we get from some random port some sort of reply, so but without any content. This is strange. Well, we can play with this later. Having a check here is not wrong in either way. We can remove the loop since it's already now it's working again. It just fails. I guess what's happening here in this case is that if the socket is if the port is completely unopened and the operating system receives a request on that port, it will reply on with a with a special sort of package saying that there is nothing to connect to there, and this then leads to unlock this wait for ready read. But and the sender, we could convert this to string so that we see what was it. So q string test. It should still be then localhost. Right, so the other one is not running. We should run in the situation where this will not be blocking and we get some random reply. Alright, we already used test. Let's call it sender string then. Okay, so the address was not. Okay, so I guess it's just fails and doesn't do anything interesting. Well, it gives us a port and always the same one, but the sender is not set to a valid address. That's probably written somewhere in the Qt documentation why it behaves this way. It's definitely not something I would normally expect. I would expect if we send something to a address which is completely not available, that at least wait for read would not be triggered. There might be a different slot that can be triggered in such a situation, but it should have no effect on wait for ready read. This is not a nice architecture at this point. Okay, so we have seen how to use UDP and TCP. Of course, doing the same, something similar can be of course done directly with the normal Windows API. So I don't know if this is interesting for you. If not, then what we can also do is we can take a look how else we could communicate between two processes on the same computer. So of course you can on the same computer also use a network, as we have seen here with the localhost address. This works quite reliably also, even though the Windows firewall is asking for whether to permit or not communication. I think it by default would not block effectively localhost communication, so it would block real outbound and inbound communication, but not what happens on the same machine. And if you want some dedicated, but you might want some dedicated communication method, not using or abusing network. And on Windows and on Linux there are ways of doing it. You can create so-called pipes which allow you to send data from one computer to another. And on Windows you can even select a mode of operation if you want them to be more message based, or if you want them to behave like a TCP connection where you just pipe in data on one end and they come out on the other. So one thing to keep in mind about the way TCP works is that if you send like a couple of strings after each other in quick succession, on the other end you will not have this. You will not necessarily have the same amount of REDS-V invocations, but you might just get one and then get all the strings in one sausage, just end-to-end connected. So usually when using TCP you would implement some own protocol on top of that, which will, for example, always prefix every message with a message ID and a message length and then the payload, and then the next message ID, message length, payload, and so on. With UDP you don't have this behavior. If you send in 10 packets you will get the 10 packets out, or well, less if some not arrive, but it will never bunch anything together. And with pipes on Windows you can actually select the operation mode, so whether it will just bunch things together and you have just one stream of data, or if it will keep individually messages put individually on the pipe as one individual message, so that even if it could bunch things together it won't do that. So let's start with that. So we will need yet another project. Today we are creating a lot of very small projects, but I think it's quite entertaining, so we call it pipe server. And at least on Windows, pipes work quite differently than sockets with regard how to accept connections. So on with network with sockets, you have like one listening socket which is dedicated for listening, and then you just can get as many connections in as you want, and then new sockets are created. With pipes, it works on the server side. It works like that: the server opens a certain amount of pipes, all with the same name, and then if one of the pipes gets connected to, it is connected, and then it opens a next pipe in its place to listen for connections. So it's kind of different behavior. For simplicity, of course, we can go with just having one pipe waiting for incoming connections, and unless we expect many incoming connections at the same time, this is good enough, because the time window where there will be no pipe ready to receive an connection will be very short. But of course, if we would implement something where we expect multiple connections, then we should just have a set of multiple open pipes ready to connect at any point in time. With Qt, by the way, it is quite trivial, because you just do the same thing as in the TCP server and TCP client example, but instead of TCP server, you are using QLocal server, and it abstracts away all the complexity. So you just specify the server instead of a port and the address. You just specify the pipe name, and I think there is a parameter where you could specify how many pipes it should open in the background, but you don't need to use it, and it will do it for you automatically, and the rest will behave identically. It will be a QLocal socket instead of a QTCP socket, but it will have the same functions. The function will behave identically, so it's quite convenient. While here, of course, we need to manually do everything. So we will include a few things which we need. First of all, Windows H. And we will see what else we will need. So actually, this could be inside the loop already. Make just an endless loop for receiving new connections. Pipe ist gleich create named pipe, and it takes a name. So L backslash pipe. And with the Qt server, you would only specify the name mypipe. This prefix, it would automatically add. So if we have enough time today, we can, otherwise we only have half an hour left, we can try also a Qt pipe server. Or if we don't manage, then the Qt pipe server will be homework. That's also a good idea, since it's quite trivial in comparison, because you don't need to specify all these different special magic values, which only the documentation can tell you how to properly pick. So duplex means we can send and receive. Pipes can be also unidirectional. Type message. So as mentioned, if we send multiple messages, we want them to arrive as multiple messages instead of being bunched together into one large blob if we are too busy reading it. Read mode message, and we specify that it should be a blocking pipe. And unlimited instances, and we will need a specify a buffer size. Say 512 bytes should be enough. Or let's go with more. Let's go with a page. So what was that? Output buffer size, input buffer size, timeout. we don't want any timeout, so 0. And security attributes null, so we allow anything to connect to it. Of course, if this for some reason fails, invalid handle, invalid then we break, but it shouldn't fail. Okay, and connect in pipe. This is kind of like our listen call. It will, or how like our accept call, or it's kind of both in the same way. So we have created the pipe, and we just kind of here wait until it gets a connection or until it fails. Null. Okay, so and this returns true or false. So if this is true, then true, and if this is false, you want to check get last error for being error error pipe connected. If you look into the documentation, the function might return an error and then still say that it managed to connect. So this is kind of weird. Why it works this way. Okay, so if this was false, then we close handle to our pipe. Oops, pipe is here, and continue. Else it was successful, then we create again a server thread. So let's just copy this and that. And we have a, here of course we pass the pipe as an argument instead. And inside this we will of course here close handle pipe, and this will of course be a handle. The content will be erased, so this will need to redo. Char. Okay, the buffer we could have kept 0x plus 1. The double word read bytes 0, and here we use the read file. So if exclamation mark read file pipe comma buffer comma Caesar of buffer -1 comma reference of read bytes and null. Okay. Again, if it fails, then we just break, and then we just send the same thing out which we just received. We just need and this will be write file, and here we will have of course the byte spread. Okay. Yeah, so it does the same as the other one. It just prints the thing again, and we want to here print this to the console as well, so that we see what's there. So this we can already start, but it will not be doing much as we are missing the client. So let's create the pipe client. Right, console application, pipe client, and the client is much simpler. It does only have one function. Pipe server, copy this, Okay, so let's see how we do that. We need to connect, but the connection might not work instantly, so we create a H-pipe and initialize it with invalid handle value. Now we make a loop that will try to connect. So the idea is that if our server is made as we did it, that it only has like one pipe, and some other client is right here in process of connecting before the next pipe is created, that we want on the client side to fix this, so that the client just tries a couple times to connect to the pipe and then only bails out if that really fails. So a pipe is new, and this time we use create file to access it, so it's not quite analogous to here. So this create named pipe this create named pipe is used when you want to create a pipe, but if you want to connect to an existing pipe, you just use create file, or you could actually use also open file. It will be just as fine. This one has much less arguments. Let's stick to the create file, because for this I know which arguments we need. L, and again backslash 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 backslash. Actually, we can copy it by typing zack. Okay. And what do we need? So what do we want to do? Access, we want generic read and generic write. Then share mode is 0. Security attributes is null. Create disposition open existing 0. That's a null. We could have probably used open, and we will try later to change it to open and just drop the access parameters. So if pipe is not equals invalid handle, then we are done. We succeeded. Else we have to check what went wrong. So if get last error is unequals error pipe busy. So if the error is not pipe busy, because pipe busy is what we would get when this would happen. So here, in principle, we could instead of close handle, I think we could disconnect the pipe and reuse it, but we're not doing it, so the pipe will stay busy. But if it was the busy error, then we just try again. But if it was not the busy error but something else, like if the server wouldn't be started, then it would be a different error. So then we want here just to break. And so at this point, if we arrived at this point, we know that the error was pipe busy. So now we can wait named pipe. So we can wait for a pipe with a given name to become available. We can specify timeout. Let's go with 20 seconds. So if this is successful, we are happy, and we repeat the loop trying to connect. If this returns false, then we break, because apparently the server is busy still, and something's not right, so we just break. So okay, so at this point we check whether we managed to connect. If we did not, then we return. If we did, then we can start using the pipe. So we want still use this message mode, as it's much more convenient. Set named pipe handler state. Set named pipe handler state. H pipe comma mode reference mode comma this we don't care about. Now we can already write to it. Of course we expect written bytes to be as much as we tell it to write, but it always has a certain probability that for some reason it fails, so we keep it. And for buffer test comma here comma number of bytes written, it will be reference on this comma and null. This overlapped structures, it would be if we would want to use this in a non-blocking mode, but since we want it blocking, then we don't care. Buffer. This we can actually copy from the other. So if this is successful, then we set 0 and printf the thing. Okay, and when we are done with this, we can close handle and down and return. So now when we run it, we expect it to write test in this console and test in our own console. Well, it didn't work. Let's see why. Okay, it connected successfully. Ah, the check is wrong. It should be if it's equal. Obviously, if it's invalid handle, then bail out. Yeah, it's working. Okay. So I think this is enough of the demonstrations. I think what would be nice would be to now think of some homework, and I think since you saw the example how TCP server works, it would be a really nice homework if we would let you implement the 24 10 2024 implement the a Qt based pipe server. As said, it is quite analogous to the TCP use case. You can just go on the documentation site for so let's write it down. Homework from the links. Q let's call it Q local server in the pipe server project. And pipe project comma the prefixes. So you create just a local server, and on it you can start call the listen function. So just like here, just that this listen will take a string instead of an address and a port, and the string to listen on will just be the name itself, my pipe, and that's it. And of course to connect to, you use QLocalSocket, and QLocalSocket has a connect function which just takes the name. Though I am not sure. Let's see. Okay, it will not be just connected, and it will not be connect to host. It will be probably connect to pipe or connect pipe or something like that, or connect to server. You see here, connect to server name. You can specify optionally here read mode, but the default read write is fine. So use clock token in. Thank you. Okay, I think this should be simple enough to do. You just need to repeat the steps we had with this TCP server and adapt the example accordingly. And maybe as an optional assignment, add a list in the pipe server UI all actions, optional A and B. So on the server we want just to see all the connected connections, and on the client we want to be able to send the individual lines. I think this should be, and as mentioned, optional assignments are optional, so you don't need to do it, but it's good to do it as it gives bonus points. Any questions? Okay, if there are no questions, then I'll upload all these projects to the Moodle and the recording, and we will see each other next week. Have a nice weekend. Bye bye.